Well, guys, here you go. The topic for today is on the board. The date today is the 11th. As you guys are getting settled, let me just tell you, your tests are graded. They're not in Skyward yet. Frankly, I did that on purpose. I'll enter them by the end of the day. But I will be handing them back to you at the end of the class today. Guys, let me just tell you while I'm thinking about it. 73 points on the multiple choice, right? 73 bubbles you filled in. And then on the back, there were 6 Lewis dot structures that you drew at 5 points apiece. 6 times 5, 30. 73 plus 30, 103. Guys, here's what I did. I just added your points. So you could have got more than 100% on the test because I gave you those 3 points as extra credit. Frankly, I haven't seen your scores. My TAs totaled your grades, but I had several. The only class I've handed back is A4, and there were multiple people that got scores over 100. So if you see a score over 100, that's why. There are 3 points of extra credit built into the test. Retests, guys, are next week, Tuesday, Wednesday, and Thursday. Check the calendar for locations. And guys, remember, this is the last test on second quarter's grade. Don't expect another test to dig you out of a hole. So when in doubt, if you've got time, take the test. So you guys all caught up with me? You're good? Okay. So guys, let me explain to you what we're going to do today. Today's kind of an interesting hands-on kind of day. You don't need to write this down, but here's the idea. Guys, last time what we did is we learned about covalent bonds. We learned about polar covalent bonds. Those are the little arrows. And then we learned about the polarity of molecules. And what we found out is that polar bonds lead to polar molecules if the molecule is not symmetrical because it either has unbonded electrons or it has different atoms around the outside of it. So now I understand, I think I understand that you guys are doing well with this idea of polar molecules. Well, guys, what we're going to do today is we're going to talk about what happens when these polar molecules get together in large groups. So, for example, if you have a bunch of methane molecules, you drew these in homework, what do these do when they get together in large groups? You're going to find out the answer is not very much. But then, guys, what happens when a bunch of water molecules get together in large groups? And then we're going to talk about what happens when a bunch of methanol molecules get together in large groups. And we're going to figure out how these things behave on a big scale because of their small scale polarities. So, guys, in order to do that, what we need to do is talk about this very important topic. So this is where you want to start taking notes. Guys, these are what are called intermolecular forces. Let me just tell you right now, this is the hardest topic that you will get into in AP. The AP authors love to pick at intermolecular force questions because you can reveal hundreds of different misunderstandings by asking one question. So this is kind of a crazy, big topic in AP. We're going to narrow it down to some very not simple, they're important, but some fundamental ideas that I think you'll all be able to get your arms around. So guys, at the most basic, what is an intermolecular force? Well, the bottom line is this. When you get polar molecules together in large groups, what they do is they attract each other, just like magnets. Magnets have a north pole and a south pole, and the north pole attracts the south pole. Well, guys, polar molecules don't have a north pole and a south pole. They have a positive dipole and a negative dipole. But just like magnets, they attract each other. So the idea is that the positive dipole from one molecule attracts the negative dipole of another molecule, and vice versa, and they all stick together, and that influences the way they behave. So guys, what you're going to find is that today is going to start with just a bunch of background notes, and then this is quickly going to turn away from writing and towards thinking. But for now, it's just going to be some things you need to get. So here's where we are. So polar molecules, when they get together, they attract each other. Just like magnets with the north and south pole, these polar molecules with the positive and negative dipole attract one another. Now guys, the name of this attraction is what is termed an IMF, an intermolecular force. Inter means in between. So inter, in between, molecular, molecule, force. So it is an attractive force that exists in between molecules. We'll call them IMFs for short. Feel free to abbreviate when you refer to them. Even when you speak of them, it's okay to just call them IMFs. It's a little easier. But guys, the bottom line is this. These attractive forces that exist in these substances, because the molecules are polar, are called intermolecular forces or IMFs. Now guys, these attractions are not very strong. They're actually about 1/10 to 100th the strength of a covalent bond. But guys, don't confuse weak with not important. They're wildly important. They're just not terribly strong. So these intermolecular forces are not as strong as bonds. They're not intermolecular bonds. Don't refer to them as bonds. They aren't bonds. They're simply attractive forces that exist between these molecules. And again, they're not very strong. But they don't all have the same strength. So what determines the strength of the bond? The polarity of the molecule. The more polar the molecule is, the stronger the intermolecular forces will be. That's why I ask you question number 16 in the homework. How do we figure out how polar the molecules are? By subtracting the electronegativities. So we figure out how polar the bonds are. That will tell us how polar the molecules are. The more polar the molecule, the stronger the intermolecular forces. So again, guys, that's why number 16 was important. If you look at the two atoms and subtract their electronegativities, and it's a huge value, you're going to have a really polar molecule. But if you subtract their electronegativities and it's small, you're going to have a molecule that isn't that polar. You guys good? Okay, so here's where we are. We are now understanding that we're talking about how polar molecules interact with each other. What we're finding out is that they attract each other. The positive dipole from one end literally attracts the negative dipole from another end, and they stick together. And these sticking together forces are called intermolecular forces. We learned that they are not very strong, but they are very important, and we learned that their strengths are not all the same. The more polar the molecule, the stronger the intermolecular force. You good? Okay. Guys, basically now you're done taking notes. Sort of. Well, no. I'll have you define the things we're going to look at, and then you'll be done. So guys, this is what we're going to do with this today. So what we're going to do is we are going to talk about, and actually you should write this down. I was going to have you skip it, but I thought better of it. Guys, what we're going to do is we are going to look at how the strength of the intermolecular force determines the physical properties of the substance. So substances with strong intermolecular forces will behave in one way. Substances with weak intermolecular forces will behave differently. Now guys, this is where we're going to narrow this down compared to what you have to learn in AP. In AP, there's all sorts of stuff that you've got to wrap your head around. In this class, you only need to understand 4 of these properties. So what we're saying now is intermolecular forces determine the properties of these substances, but you only have to be able to keep track of 4. The first one is phase. You guys all, of course, know the 3 phases of matter, right? Solids and liquids and gases. So guys, what determines if a substance is a solid or a liquid or a gas? And the answer is the polarity of the molecules. because the polarity leads to intermolecular forces, and the intermolecular forces determine if they will be solids or liquids or gases. We'll talk more about that in a minute. This is going to be our laundry list of what we're going to do today. So guys, thought number one is this: the strength of the intermolecular force determines if a substance will be solid, liquid, or gas. Then, focusing on the liquids, there are three things that you need to know about liquids and how that relates to intermolecular forces. These are things that you're going to want to define because I don't know that they'll be terms that you necessarily understand. So the first is volatility. Again, guys, these terms apply to liquids. So what does it mean if a liquid is very volatile? What it means is it evaporates very quickly. So guys, volatility refers to the ease with which a liquid evaporates into a gas. And what you're going to find out is this all relates back to intermolecular forces that relates back to polarity. So guys, let me just tell you right now, in order to be successful today, you've got to use the word therefore. When you are answering these questions, you need to be able to use the term therefore. This molecule is very polar. Therefore, it has strong intermolecular forces. Therefore, what does that say about volatility? Because these are all cause and effect relationships that you're going to have to think through. The next one is this: boiling point. Boiling point is the temperature at which all the molecules in a liquid have enough energy to vaporize into a gas. And as you might guess, boiling point also depends on intermolecular forces, and intermolecular forces also depend on polarity. Then guys, two more, and then what we're going to do for the rest of the day is we are going to pick 3 sample substances that we're going to talk about relative to all these ideas, and then we're going to go through this with each one of these characteristic properties. So guys, the next one is cohesion. This one you probably know from biology. Cohesion is the attractive force that exists within a substance. And then guys, you can contrast that with adhesion, that is the attractive force that exists between two different substances. I think in biology you learn about capillary action, maybe. That's the result of adhesive forces. So guys, there you have it. That's our laundry list for today. We are going to talk about now how polarity leads to intermolecular forces, and then how these intermolecular forces, first of all, determine if a substance will be a solid, a liquid, or a gas, and then how the liquids behave because of intermolecular forces dependent upon volatility, boiling point, cohesion, and adhesion. Once we've gone through the list, you guys are going to have time to do your homework. You guys ready to go? You're good? Is everyone caught up? Okay. So guys, the first thing that we need to do is we need some substances that we can talk about. So these are going to be our 3 subjects, if you will, that we're going to talk about. So guys, what you need to do is draw their Lewis dot structures into your notes and make this as wide as your paper. So this is CH4, this is CH3OH, and then this, of course, is water. Now, guys, it's up to you how you handle this. If you want to try to sketch this, sketch these, that's totally fine. If you'd rather draw the Lewis dot structures, that's fine. But you need these 3 molecules in your notes, make them big, and then draw in their polarity arrows. So again, the choice is yours. Whether you draw Lewis dot structures or whether you physically try to sketch these molecules is totally up to you. But guys, notice, even if you draw the Lewis dot structures, just like you did in today's homework, draw them as realistically as possible. So when you draw CH3OH, draw that bond between the carbon and the hydrogen around oxygen bent, because it's bent. There are 4 domains on that oxygen and only 2 of them are bonding, so that would be bent. That would be my phone. Would you take a call from Rockville, Maryland? Not gonna happen. Not gonna happen. You guys all caught up with me? Not yet? All right. How about now? Are you guys, and you all need to be ready to go because we're going to start drawing arrows into these and talking about them. You guys good? I'm going to go unless I hear something. All right. So guys, here's what we need to do. And we'll just do this together. We need to identify the polarities of these molecules. So let's start on the right with CH4. What direction does the polarity arrow go in CH4? It doesn't. Guys, that molecule is symmetrical and therefore nonpolar, right? Each one of these bonds is polar. I don't remember which one's more, is carbon more electronegative? I don't know. Anyway, doesn't matter. Because the molecule is symmetrical, this molecule is nonpolar. So if my board will allow me to do it, we will label it as such, as nonpolar. Okay. Now guys, what we need to do is we need to identify the polarity arrow for the next one, which is CH3OH. So the first question is this: is it nonpolar? Is that thing symmetrical? Heck no. There's no way that thing is symmetrical. So if it isn't symmetrical, we now know that it's got to be polar. So now, how do we know which way the arrow goes? Well, we need to know the electronegativities. So I just looked up the electronegativities. We know that water is going to be polar too, so I put them there as well. But guys, now that we have the electronegativities, we can now start drawing in polarity arrows. So guys, which direction is this bond going to move? Towards the oxygen or towards the carbon? Towards the oxygen. So this bond will move in that direction. Now, which direction will the bond between the oxygen and the hydrogen move? Also towards the oxygen. Now guys, what about the bonds between the hydrogen and the carbon? Well, carbons or hydrogens is 2.2, so all of these are going to be closing in this direction. Now guys, we've never done anything this complicated before, but I think we can think through it. So start on the left. What direction is this entire mass moving? In towards the carbon. Now, if we assume that these are all moving in towards the carbon, which direction is the carbon moving? Towards the oxygen. And which direction is the hydrogen moving relative to the oxygen? Towards the oxygen. So we've got this and this and this. So what is the overall direction of that movement going to be? Up towards the oxygen. So it would be that. And then, guys, finally, let's take a look over here at our good friend water. This is polar in this direction. This is polar in this direction. Now, what about the polarity of the overall molecule? How do we draw the arrow? Up. You got it. Okay, so guys, all of that, except for this little interesting complexity, guys, all of that was review from last time. Do you need to ask questions about any of this with the understanding that we sort of just did this homework assignment? You guys all okay? Because now we're going to do something different. So guys, the thing that we have said today that we didn't talk about last time is, yeah, we understand that some molecules are polar and some aren't. But what we need to do now, given the conversation that we just had, is realize that these two molecules don't have the same polarity. We understand that CH4 is nonpolar and that these two are polar, but now we need to talk about how their polarities compare, because they're not the same. So guys, in view of question 16 from the homework and in view of the things that we just talked about, we now need to talk about which one of these is more polar. So here's what we're going to do. Let's put these three molecules in order by increasing polarity. Number one is going to be the least polar. Which one is that? Which one is the least polar molecule on the board? Nonpolar. Guys, this is number one. That is the least polar molecule on the board. Now, which one is the most polar and which one is the middle polar? Well, guys, what is it that determines, again, thinking about question 16, what is it that determines the polarity of the molecule? The polarity of the bonds. And what is it that determines the polarity of the bonds? The difference in their electronegativities. So guys, let's compare. We understand that this molecule is polar in this direction. So we can sort of say that the polarity is the result of this bond and this bond. And then this molecule is polar in this direction, and it is the polarity of these bonds. So the molecule that will be the most polar will be the one with the bonds that are the most polar. So now let's compare. Well, guys, we can ignore one of these oxygen-hydrogen bonds because both molecules contain it. So now we've got to look at these bonds. This oxygen-hydrogen bond and this oxygen-carbon bond. Which is more polar? Oxygen-hydrogen or oxygen-carbon? Why oxygen-hydrogen? Because hydrogen is weaker than carbon, and they're both bonded to oxygen. The difference here is essentially 0.9. The difference here is essentially 1.2. So this bond will be more polar than this bond. So this molecule is more polar than this one. So guys, this is the most polar molecule, and this one is in between. You get the idea? All right. So now, guys, let me show these to you in 3 dimensions, and then we're going to play with them. So this is CH4. That is, oh, yep. This is CH3OH, and this is H2O. You ready to go? All right. So, guys, what we're going to do now is we're going to go through that list. Now that we know their polarities, how does that affect their phase? Now that we know their polarities, how does that affect their volatility, their boiling point, and their adhesive and cohesive forces? And by talking about that, you're going to understand those concepts. So guys, here we go. First of all, phase of matter. Stop taking notes. Just watch. So guys, let's start with our least polar friend. Our least polar friend is CH4. What do you know about the polarity of CH4? Non-polar. So guys, when you get a bunch of these nonpolar CH4 molecules together, right? When you get a bunch of these nonpolar CH4 molecules together, what do they do to each other? Nothing. They just spread out. If you don't believe me, listen close. I am now filling the room with nonpolar CH4 molecules. Because, guys, natural gas is just a steady stream of CH4. And you've got all these molecules pouring out of this Bunsen burner tap. And what are they doing? They're going, woohoo! And they're spreading out all throughout the room. Why don't they clump together? Because they're nonpolar. And because they're nonpolar, they don't exhibit intermolecular forces. And because they don't exhibit intermolecular forces, they all spread out in what phase? A gas. And guys, that is true of all nonpolar molecules. All nonpolar molecules are gases. Why are they gases? Because they don't have intermolecular forces and they don't stick together. So guys, this is what you need to write down. This is the way we're going to summarize that. If you have no polarity, if your molecule is not polar, guys, notice the arrow. You know what that arrow means? Therefore. If you have no polarity, therefore, you will have no intermolecular forces. And if you ain't got no intermolecular forces, what phase are you going to be in? Gas. And guys, that works in both directions. If you have a nonpolar molecule, it will be a gas. If you have a gas, you know it's a nonpolar molecule. Guess what the homework questions are going to look like? Just like that. If you got a gas, it's nonpolar. If it's nonpolar, it will be a gas. It works in both directions. You good with that idea? Okay, so let's bring in number, yeah, go ahead. That are not, okay, and so here's the thing, Josh, that we should say more carefully. At room temperature and room pressure. Because, I'm going to throw this at you, so catch it. If you slosh that around, there's a liquid in there, right? And that liquid is air. That's actually liquefied air. So we understand, right, when we breathe air, it's nitrogen and oxygen and carbon dioxide. And because these are gases, what do we know about nitrogen, oxygen, and carbon dioxide? They're all nonpolar, right? That's why they're gases. But the idea is that if you put them under enough pressure, you can actually get them to turn into a liquid. And that's what's sloshing around inside of there. And if you pull the trigger, the pressure comes off and it comes back out as air. So, I mean, if you'd just be breathing air. So the answer is, yeah, you can take nonpolar molecules and turn them into liquids. And even solids, you just have to compress them really hard. So, yeah, interesting stuff. All right, you guys good on CH4? All right, so now, guys, let's pull into the conversation our middle guy, CH3OH. So you ready? Same question. When we get CH3OH molecules together, here's two of them. We're going to talk about billions of them, but let's just talk about two. Are these molecules polar? Yes. So will they have intermolecular forces? Yes. So will they attract each other? Yes. So will they be a gas? No. You know what they are? They're a liquid. Guys, this is not water. There is no water inside of here. Inside of here is just a bunch of these. This is methanol. This is what is called wood alcohol. You drink it and you go blind. Guys, this is wood alcohol or methanol, and that's the only thing that's in here. But why is this a liquid? Why? It's because these are polar. See, guys, these polar methanol molecules stick together and it causes them to be a liquid. Why do they stick together? Because they're polar, and these polarities cause attraction, cause intermolecular forces, and it sticks them together as a liquid. You get the idea? So what's the relationship? If you have polar molecules, will they have intermolecular forces? Yes. And if they have intermolecular forces, they will, in this case, be a liquid. Now, guys, what about the solids? Even stronger intermolecular forces. You'll find out in a minute I didn't give us an example of a solid, but just so you know, if a substance is a solid, you know that those particles are even more polar. But we're good with this idea of this being a liquid, right? Okay. This is why I didn't choose to do a solid. Let's do our good friend H2O. So guys, when you get a bunch of H2O molecules together, are these molecules polar? Yes. So will they stick together with intermolecular forces? Yes. So will they be a gas? No. So what are they? They're a liquid. So you know what? Let me get some. And sure enough, there you go. And there is our liquid water. So guys, again, I don't think you need to write this down because the same trend holds true. Don't write it twice. If we have a polar molecule, like water, it's got intermolecular forces and it will be a liquid. So guys, why did I not choose to do a solid? And why did I choose to do two liquids? Well, guys, the answer is this. If you go back in your notes, we said that the things we're going to talk about are phases and then volatility, boiling point, adhesion, and cohesion. But volatility, boiling point, adhesion, and cohesion are all properties of what? Liquids. That's why I chose two liquids. Oops. Guys, I chose two liquids because now what we can do is we can use these two liquids and we can talk now about adhesion and cohesion and volatility and intermolecular forces. So guys, again, the idea is if the forces were even stronger, it would be a solid, but I didn't choose that because having two liquids will now allow us to talk about the rest of the stuff. Get the idea? All right, so here we go. Guys, the next thing that we're going to talk about is volatility. So we can put methane away because methane doesn't play this game because it's a gas. So again, guys, if you need to go back in your notes and remind yourself, do that really quickly. What is volatility? The ability to do what? Evaporate. Now, guys, let's talk about what causes a substance to evaporate. And in order to have this conversation, guys, you need to take a look at something like this. This is actually sort of a representation, if you will, of the surface of both of these liquids. Whether it's the water in the beaker or whether it's the methanol in the flask, it doesn't matter. Guys, both of these liquids has a surface. And at that surface, there are molecules that are right at the surface that would like to jump out. But what is keeping them from jumping out, represented by those arrows? Intermolecular forces. So guys, right at the very tip, at the very top of this water, there are molecules that are sitting there going, I want to jump out, but I can't because all my buddies are holding me back because I'm attracted to them by intermolecular forces, and I can't jump out because they won't let me. You get the idea? Now, here's the deal. These two liquids do not have the same volatility. Remember, what does volatility mean? Ability to evaporate. So guys, what I'm going to do is I'm going to pour a little bit of water there, and I'm going to pour a little bit of the methanol here. And what happens, I tried to pour equal sized puddles, and what is happening right now is these things are evaporating. There are, in fact, some molecules of water on the surface right here that can actually break the intermolecular forces and go, woohoo! and evaporate. And there are some methanol molecules that can break the intermolecular forces and jump out and evaporate. And again, what's keeping them from evaporating? Intermolecular forces. Now, what do you know about their intermolecular forces? Are they the same strength in water as methanol? No, which one's stronger? Water. So which one should have a harder time evaporating? Why the water? Because the molecules have stronger intermolecular forces and it's harder for them to jump out. Well, guess what, guys? It's actually true. To speed this up, I'm going to spread these out. And you can, I don't know if you can see this or not, but you can actually watch the methanol evaporate. You can, it's almost gone. I mean, I don't know if you care to see, but you can even stand up if you want. But guys, you can actually see this puddle just going away. This is almost dry. We could come back at the end of the class. I'll leave it. That's going to be wet until we're done. And guys, this is almost evaporated. Why did the methanol evaporate so much more quickly than the water? What do we know about methanol? Weaker intermolecular forces. And guys, why does methanol have weaker intermolecular forces? Lower polarity. Guys, you've got to be able to connect those three concepts. Lower polarity, weaker intermolecular forces, higher volatility. Let's put it in print. This is dry, by the way. So guys, we're going to look at it from the other side. Higher polarity. Which one's got a higher polarity, water or methanol? Water is more polar. Therefore, what will be true of its intermolecular forces? Stronger or weaker? Stronger. And if its intermolecular forces are stronger, what will be true of its ability to evaporate? Higher or lower? Lower. Guys, this thing is still as wet as the second I did it, and the methanol's all gone. So guys, if this is true, we know that the opposite is true. Lower polarities, like methanol, lower intermolecular forces, and higher volatility. So there's one. You feeling good about the connection between volatility and intermolecular forces? So let's go number two. Number two, guys, is boiling point. Remind yourselves of what the boiling point is if you need to look back in your notes. Boiling point is the temperature at which all of the liquid can turn into a gas. So guys, what determines the temperature at which this is going to happen? Well, here's our picture again. In order for any of those molecules to jump out and boil, what do they have to do? Break the intermolecular forces. So guys, think about it. If we wanted to take this beaker of water and boil it, what do we need to do? Add energy. What does that energy do to these molecules? Do you guys know? Makes them move faster. And eventually, they move fast enough that they can break and jump out. So how is that different from evaporating? Well, guys, when a substance evaporates, some of the molecules have enough energy. When a substance boils, all of the molecules have enough energy. You see the difference? That's the difference between boiling and evaporation. So what's the connection? So again, guys, if we have, and you want to get this in your notes, if we have a molecule that is very polar, what do we know about its intermolecular forces? Are they weak or strong? Come on, guys. High polarity, what do we know about intermolecular forces? Strong. They're way stuck together. So guys, if they are way stuck together, will it be easier or harder to get it to boil? Harder. So we will have to heat it up to a higher temperature. So the boiling point goes up. So guys, you ready for a deep thought? And you don't need to write these numbers down, but just think through this with me. Remember, we've got three samples, right? We've got water, we've got methanol, and we've got methane. Which one of these is most polar? The water, the methanol, or the methane? The water. So, it's got the strongest intermolecular forces, so it should be the hardest to boil, so its boiling point should be the highest. Guys, what's the boiling point of water? 100 Celsius, right? So if this is the most polar and therefore the hardest to boil, what would the boiling point of methanol be compared to water? Higher or lower? Lower. And in fact, it is. It's actually 65 Celsius. That's like crazy hot tub water. Now, it would hurt if you got in there. It's a little hotter than hot tub water. But guys, what about this? If this is true, what should then be the boiling point of methane compared to methanol? Higher or lower? Even lower. And guess how low it is? Ready for a deep thought? It's lower than room temperature, which means that it's already boiled. The temperature is actually negative 161 Celsius. So guys, you can think about that through kind of another interesting way. That the reason that methane is a gas is because it boils at a temperature below room temperature. And again, that comes back to the reason that it's nonpolar. You good? Yeah? It means it's a liquid at negative 161.1 degrees Celsius. Yeah, yep, yeah, crazy, huh? You guys good? Yeah? 22. So 20, did I tell you about this? I'm trying to personally adopt the metric system. Everywhere that I can, like in my truck, it has a little temperature readout. I've switched it to Celsius. I actually took a little label printer and printed the kilometers per hour speeds over my mind. I'm trying to switch to the metric system. Frankly, largely because I'm a cyclist and all of the cycling comes out of Europe and they're all on the metric system. So when I'm watching a race in Abu Dhabi and it's 40 degrees Celsius, I don't know if that's hot or not. So I'm trying to switch. But so 75 Fahrenheit, about room temperature, is about 23 Celsius. So, yeah. You guys good? One more to go. Ready? I get to show you pretty pictures. Guys, the last one is adhesion and cohesion, and we are going to do them together. So remind yourselves, what is cohesion? Something sticking to itself. What is adhesion? Something sticking to something else. But whether it's sticking to itself or whether it's sticking to something else, what is the force that makes it stick? Intermolecular forces. Guys, that's how glue works. When you glued those stupid little boxes down to your periodic table lab thingy, which is kind of a fun lab, but what you were doing is you were adding intermolecular force substance. We call it glue. And what happens is that intermolecular force substance, glue, creates intermolecular forces with the paper in both directions and sticks it together. Guys, that's how glues work, is by reaching out through intermolecular forces and sticking things together. So what do you now know to be true about the molecules in glue? They're polar, right? Because if they weren't polar, not only wouldn't they be sticky, they'd be gases. Okay, so guys, with that said then, check this out. What is represented right here in this picture? What do we call that dip? The meniscus. Now guys, let's talk. This is a zooming in of the meniscus, just the left side of it, but a zoom in on the meniscus inside of a test tube or a graduated cylinder. So what's going on here? Well, these water molecules are being attracted to the glass. What is that force of attraction? They are intermolecular forces, and they are drawing the water up the sides of the glass. So what do you now know to be true about the molecules in the glass? They're also polar, and those forces of attraction draw the water up the side of the glass. Now guys, what do you suppose would happen if we put methanol in a graduated cylinder? How would the meniscus look different? It wouldn't be as tall because this substance is less polar, therefore it's less attracted to the glass, and the meniscus wouldn't be as tall. Huh? So what about this one? What about water droplets? Well, guys, when you've got a water droplet, what you actually have is a skin, if you will, on the top of the water. And that skin is also created by these forces. These are what are called adhesive forces because it's water to water, and these molecules are attracted to each other, and it creates a skin, and that skin allows water to form droplets. That would be an example of an adhesive force. But probably the adhesive force that you think of the most is what we call surface tension. And guys, you may want to scratch that idea in your notes. Surface tension is an example of an adhesive force. By the way, guys, this table's still wet. The water still hasn't evaporated. But guys, how does surface tension work? Well, these water molecules are all attracted to each other. That attraction causes a surface that is actually strong enough that the leaf can float. So if this is water attracted to water, that would be a cohesive force. Co means with the same, adhesive means with the other. So guys, surface tension would be an example of a cohesive force. So guys, what about this? What if we had a lake full of methanol? Would the surface tension be weaker or stronger? It would be weaker, and therefore some things may not float that otherwise would. Now, you ready for kind of an interesting little thought? Guys, this is how soaps work. What a soap does, well, one of the things that soaps do is actually break the surface tension of water. Because in order for water to clean your clothes, you've got to get the water to not be attracted to itself. You've got to get the water to be attracted to the dirt. So one of the things that soaps do is break the surface tension of the water. Don't do this. Well, you can do this in a bucket. Don't do it in a stream. But guys, you can actually do this. It's kind of interesting. Take a bucket of water and float something on it, like a leaf, or you can even, have you ever seen where they make compasses by floating a needle on the surface of the water? Anyway, whatever you want to put on there, something that's resting on the surface tension. And put a drop of soap into the bucket and it falls right to the bottom. Because the soap breaks the surface tension and it'll fall right to the bottom. I've actually seen videos of this where, have you seen water striders, those little bugs that can walk on the surface tension of the water? And you put a drop, it's kind of mean, but you put a drop of soap on the water and all the bugs drop to the bottom because they can't, it breaks the surface tension and they can't stand on it anymore. Don't do that in a stream because you just polluted the water, but it does in fact work. Okay, so what's the connection? Well, again, guys, this all comes back to polarity. If you have molecules with high polarity, they have high intermolecular forces. If they have high intermolecular forces, what will their adhesive and cohesive forces be? Weak or strong? Weak or strong? They will be strong. Strong adhesive forces, strong cohesive forces. So guys, there you've got it. Let me get you your homework. And then I want to guide you through this a little bit. Is this the last homework of the quarter? I think it is. I'll check the calendar really quick, but I think this is. Oh, did I give you too many? No. I think this may be the last homework of the quarter. Okay. There would be no meniscus, right? Yeah, and you know, so, well, you lost me with put water in it. Into a liquid. So when you said water, you didn't mean water, you meant liquid methane. So if you put liquid methane in a graduated cylinder, it would not have a meniscus. That's true. Yeah. The thing that's interesting is there are some substances that have meniscuses that go the other way, like mercury. I'll show you in a second. It turns out in mercury, the cohesive forces that connect them to each other are stronger than the adhesive forces, and the meniscus is upside down. Yeah. Oh, did I come up? Oh, yeah. Hey, guys, go over the homework with me, would you? Yeah, but it's all lab. Yeah. So, guys, take a look at this with me. So the first page looks really familiar, right? Guys, these are all the little logic, not puzzles, but logical relationships that we just described as we went through these characteristics. So for example, guys, looking at the first one, it's telling you the boiling point is high. If the boiling point is high, what has to be true of the intermolecular forces? Weak or strong? Strong, so draw an upward arrow. And if the intermolecular forces are strong, what do you know about the polarities of the molecules? High polarities, so draw an up arrow. Get the idea? Okay, then guys, on the next page, you are going to be drawing these sets of molecules. Methyl chloride, methyl bromide. You're going to draw their Lewis dot structures. Then you're going to draw in their polarities, their polarity arrows. Some of them are nonpolar. Then you are going to circle the one that is most polar and then explain how you knew which one was most polar. And guys, what does polarity always come down to if you're comparing two polarities? Differences in electronegativity of the bonds. Then, flipping over on the back, notice what it says in question number 1. So it says, regarding set 1. Guys, do this with me. Regarding set 1. So you go back a page, and set 1 is methyl chloride and methyl bromide. So, regarding methyl chloride and methyl bromide, which will have the stronger cohesive forces? See how that brings everything together? So by drawing methyl chloride and methyl bromide and identifying the one that is the most polar, you can then answer this question and figure out which one will have the stronger cohesive forces. These are pretty brilliant questions. Proud to say I wrote them myself. So guys, dig in. I'll give you your test back in about 10 minutes.